This is advanced linear algebra course, and we're in the chapter of matrix decompositions. This chapter includes SVD or singular value decomposition, QR factorization, LU and Cholesky factorizations. Each factorization will have assumption on the matrix A to be factorized. In this video clip, I'm going to give the lecture on SVD. So we're going to start by giving you an overview, the definition, and how the factors are returned. And I'm going to provide numerical example first in MATLAB. And after that, we will go over the principle behind those calculations so that you can do it by hand as well. And after that, we'll go over the application of SVD uh, in data processing, data analytics. So let's first start with the definition. An SVD can be taken on any matrix A, can be any rectangular or square, okay, any size. It says that SVD form of A is U sigma V transpose. Suppose A is M by N. The matrix U is going to be M by M, and sigma is going to be M by N, and V is N by N. The structure of U and V would be orthogonal matrices type, which means U transpose U equals I, V transpose V equals I. Their columns, the columns in U and V are orthogonal. The matrix sigma is very special. Um, it's going to be along the diagonal, it's going to be some non-negative values, sigma I. Okay, and the off diagonal entries is going to be 0. Um, for each structure of A, for example, tall case, fat case, and square case, the matrix U, sigma and V will have the following structure. When A is tall, so your sigma can be partitioned into two blocks. The first block is sigma 1 and 0. And the matrix U seems to be can be partitioned into two columns. And this is V transpose. When A is fat, when A is fat, your sigma can be partitioned into the non-zero part, and this is the 0 block, and this is going to be U, and the matrix V is going to be partitioned into two row blocks. Okay, so in these two cases, you can see that when you multiply it out, for the tall case, it takes only the information in U1, sigma 1, and V. So this is going to be U1, sigma 1, V transpose after you multiply it. And for the fat case, so it's going to be only U sigma 1 and V transpose. All right, because you're going to multiply these with this, and the 0 go away. And for the square case, that's going to be a simple one. This is A, U, sigma, and V transpose. All of them will have n by n dimension, the size. Okay, so this is the structure. So why don't we go over the numerical example and maybe just see how to get these matrices, these factor in MATLAB. So here I'm gonna generate some random I. Okay, I'm gonna go over the tall case 4 by 2. This is random matrix. So I'm just calculate U sigma and V by the SVD command. All right. So this is to show that my U is gonna be 4 by 4. So I mean my S for the tall case, my singular value matrix is going to be it's going to have like it's going to be a tall matrix, and it's going to have 0 block at the bottom, and V is going to be n by n, which is 2 by 2 in this case. Okay, just to verify real quick, my U is orthogonal, so U transpose U equals I. My V is also orthogonal. Okay, and come back to the lecture a little bit. For the tall case, the information that we only need, the factor is going to be U1 sigma 1 V transpose. So So my A is 4 by 2, right? So if I take only the U1, that's going to be the first two columns. The first two columns in U times sigma. So I only need sigma 1, which is this part. Okay, so I'm gonna get sigma from 1 to 2, all right, and then V transpose. This give me the matrix A, the matrix A. Okay, so we just confirm, can we see the mouse? So we just confirm that for the tall case, all right, the SVD that you got only use the information of U1 and sigma 1. Okay, now let's A is 2 by 4, all right? So I'm going to do the same. I'm going to call SVD, all right? And now you see the structure that now, because A is 2 by 4, my U is going to be 2 by 2, sigma is 2 by 4, my V is going to be 4 by 4. And now let's come back to the lecture. In the fat case, all right, your sigma is partitioned into kind of two columns, and the most right block is entirely 0, and you're gonna need only u sigma 1 and v1. So this is my sigma 1. Sigma 1 is gonna be the most left block, and v1 is gonna be the first two columns. All right, the first two columns. So what I'm going to do is I'm going to use S the first two columns, okay, and my V is going to be the first two column transpose. These should give me the SVD factorization. Okay, so this is going to be the matrix A, the original one. Okay, so now come back to the lecture. How can we prove such a decomposition exists? Okay, so we're gonna start with some assumption on A, the setting on A. So let's suppose that the matrix A has rank R, okay, and and R has a positive singular value in descending order. It's going to review later that what are these singular values, all right? I'm going to show later that this singular value can be calculated as the eigenvalue of A transpose A. But let's just assume that such a decomposition exists. Um, so suppose you have what we call the vector u, that is called left singular vector, that are orthogonal in Rm. And we also find, if we are able to find v1 dot 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 vn that are orthogonal in Rn, such that these conditions are satisfied. So what is it? It says that AV1 equals sigma 1 U1. So U1, the left singular vector, is actually the image under the transformation in A. Okay, so AV2 equals sigma 2 U2 dot 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 AVR sigma R UR. Okay, suppose that holds. Okay, and there are, okay, in this assumption, our A is m by n, all right? So suppose we find the first R right singular vector, and the remaining one is just in the null space of A. Okay, so this condition, if it holds, you can also write it in a vector equation, because you can stack v1, v2, dot dot vr, all right, into columns of this guy, vr plus 1, vr plus 2, all the way to vn. Okay, you just stack it into this matrix, and then you write that AV, because AV1 is sigma 1 U1, sigma 1 U1, sigma 2 U2, and all the way to sigma R UR. Okay. And because the rest is zero, so this guy multiply with so it doesn't matter what the matrix U here because it's gonna be multiplied with zero. So basically we write the main condition that we're going to explore whether it exists or not, right? But we can write it in another form as a vector equation. So because you call this guy matrix U, V, you call this matrix as U, and this is what you call sigma. Okay. So basically, the SVD proof is based on the existence of the guy in the blue box, all right, or equivalently the equation in at the start. Okay. So let's see first, how can we find such U and V and also the matrix sigma? So let's calculate A transpose A. If now we're going to take assumption as well. We're going to take assumption that if such a decomposition exists, A transpose A would be, now we're going to transpose this, right? So it's going to be V sigma transpose U transpose, right, times A. And then we get this metric because U transpose U is identity. Okay. And because the matrix A transpose A itself is symmetric, right? It also proved that, I mean, the eigenvalue decomposition of symmetric matrix has to be in the form of Q lambda Q transpose, where Q has to be orthogonal. Okay, so in this particular result, we can claim that then you can take V as the matrix Q. This is in the form of Q lambda Q transpose, and sigma transpose sigma is just lambda. Remember, sigma will have a form of either this one or this one, right? And in sigma 1, it's going to be diagonal. It's going to be diagonal. So that's why sigma transpose sigma, which is taken to be equal to lambda. So so think about this, all right? So this is going to be sigma 1, sigma 2, dot, 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 sigma r, right? Let's just take an example of the tall case, right? So this is sigma, and of course, when you take sigma transpose sigma, that's going to be square, right, and 0. So that's why when you match this guy with a lambda, sigma k square are just non-zero eigenvalues of A transpose A. Okay, so this is the first step. Now let's explore A transpose. We do the same thing. A transpose, that's going to be U sigma V transpose, and then A transpose, which is V sigma transpose and U transpose. And because if V is orthogonal, this is I, and then you get this matrix. Okay. Um, what I write here is that because A transpose is another symmetric matrix, so it also has another eigenvalue decomposition. So again, I write it as Q lambda Q transpose. Okay, where you can see that now sigma transpose is going to have the same structure, right? Sigma transpose is going to have the little sigma square, all right? Suppose I write a structure for tall case, all right? So then we can conclude that the singular value are non-zero eigenvalues of both A transpose A and A transpose. Okay. V now previously V is eigenvector of A transpose A. Now U is eigenvector of A transpose. Because both of them are symmetric matrices, eigenvectors are orthogonal. So this is to show that these results have shown that if you take V as Q and take U as this Q, this Q and this Q are not the same Q, all right? It's just the notation. So it means that both U and V can be taken as orthonormal eigenvectors of this guy. So here's that's why first we have found a way to get V first, right? And the singular value from the eigenvalues of A transpose A. So the step of finding U sigma V is going to be the following. First, we calculate the eigenvectors of A transpose A. We get V1 dot 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 VR, right? And then we choose the sigma, the non-zero singular value to be, because sigma square is the lambda of A transpose A, right? So sigma is going to be the root of eigenvalue A transpose A. Next, next we find U based on this equation. We find U as AVK divided by sigma K. Just for the singular value, just for the K that the singular value is non-zero, okay? Just the R entries. Because we have assumption here that your sigma R is the last one that is non-negative, is strictly positive, sorry. The last VR, so suppose now you have found V1 dot 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 VR, and you also found U1 dot 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 UR. So the remaining one is the one that you can obtain from the null space of A, from this equation, from the null space of A. Okay. And now what about the remaining UK? Okay. Because the null space because the null space is orthogonal to the range of A, and you have noticed that U1 dot 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 UR is in the range of A, right? Because you construct it in this way. U is the image of VK under the mapping A. So this U1 dot 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 UR lies in the range space of A, but the range space of A is orthogonal to the null space of A transpose. This is from the orthogonal complement lecture, all right? If you haven't seen that, please review. So it means that if we can pick the remaining ones in the null space of A, these remaining one will be orthogonal, to the previous R vectors. Okay, that's the method of computing all VKs, all UKs. Okay. So why don't we go over the example, all right? So I'm gonna explain all these steps again with the example. So here's given the matrix A in a fat case. In a fat case, right, we expect something that is U sigma 1 and 0 and sigma 1 transpose, V1 transpose, V2 transpose. Okay. Here is 2 by 3. All right, so this is going to be 2 by 2. This is going to be 2 by 3, and this is 3 by 3. This is what we expect from the procedure. So A is 2 by 3, A transpose A is 3 by 3, right? We find the eigenvectors of, so we perform eigenvalue decomposition of A transpose A. And then we find that obviously you find only 2 non-zero eigenvalues because the rank of A is 2. A is fat, right? A is fat, is 2 by 3. So the rank of A is less than 2, of course. And we find from the numerical values of A that in this case, we find two non-zero eigenvalues of A transpose A. So sigma 1 is square root 7, sigma 2 is square root 3. Okay, so this Q will give us the right singular vector, is the matrix V. Okay, and sigma 1 is going to be this portion, the non-zero the non-zero singular values. So in the context of SVD, usually we sort we sort from the largest to the lowest one. So you write square root 7, square root 3 here. Next, how to find U? Okay, from the procedure UK, the first R entries of UK is the image of VK under A. So this is the matrix A. We get V1, all right, V2 and V3. So we write this V1 and square root 7 is the singular value. So calculate it. It turns out to be this vector. For U2, you do the same. This is A. V2 is that. V2 is this vector. Okay. And then divided by sigma 2, which is square root of 3. And that is the U2. In this example, we expect U to have two columns, and that's it. We have found U1 and U2. So you stack U1 as the first column, stack U2 as the second column in the matrix U. And that's how you arrive at SVD form of a fat A in this example. Now let's see another example of a tall matrix. Now my matrix A is tall, and we know that the rank of A is going to be less than or equal to the minimum between rows, number of rows, which is 4, and the number of columns, which is 3. And now we know that it's going to be at most, the rank is going to be at most 3. Okay. But in this particular example, I just create A that A has low rank in this example. Rank of A is 2. Okay, I generate it in that way. So let's find it. Let's do the same. We calculate A transpose A. Okay. How long has it been? 22 minutes. A transpose A is this matrix, all right? I compute eigenvalue decomposition. So then I get the matrix Q, and the singular value turns out to be, which is the eigenvalue of A transpose A, right, is the square of a singular value. So I find only two of them that are non-zero. Okay, so this is to show that you're gonna find the number of non-zero singular value as the number of as the same degree of the rank. Rank is 2, you find two non-zero singular value. Let's check the dimension again. This is 4 by 3. So when you perform singular value decomposition, you expect U to be 4 by 4, and this 4 by 3, and this is 3 by 3. Okay, this is what you expect. So it's gonna be like this is U, this is sigma 1 and 0, and this is gonna be V transpose. So for the matrix U, what you expect is gonna have two partitions corresponding to the sigma here. Okay. Okay, in this example, now you take V, right, which is Q. That's gonna be let me point again here. This is your V is gonna be 3 by 3, so it's a this matrix. Okay. For sigma, for sigma, it's gonna looks like uh, two row blocks. So this is your sigma 1, and this is your uh, eh, I think I type. I think I type. So this has there is no fourth column here. Sorry. So my sigma is only this, right? So my sigma 1 is going to be this one, sigma 1. Okay, this is the 0. Now let's find U. We follow the same step. Okay. Now we find only two non-zero singular values. That's why you're gonna find U1 and U2 from the image under V1 and V2. Okay. So I pick V1, which is this one, V1 multiply with A, and it gives me this vector. Secondly, I get V2 and multiply with A. That's going to be U2, all right, divided by sigma 1 and sigma 2. It's turned out to be these vectors. So uh, in this, of course, by the construction, U1 and U2 are in the range of A. Okay, how many columns in U that I expect to find? 4 columns. So the principle is that let's go back. When you already found U1 dot 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 UR that is in the range of A, okay, the remaining one you can pick any one to be in the null space of A transpose, because null space of A transpose is orthogonal to the range of A. Because our point here is that we just want to construct a matrix U that is orthogonal. So if you find U1 dot dot UR, you only want to find the remaining one that are orthogonal to the previous R vectors. Okay, and this is why, because the previous R vector sits in the range of A, you can pick the remaining one that guaranteed to be orthogonal to range of A. And that can be done if you pick the vectors in the null space of A transpose. Okay. So next, that's why in the next step, I I just calculate the null space of A transpose. All right, that is, so when I find uh, these two vectors are guaranteed to be orthogonal to the previous two ones. All right, you can check. This one is orthogonal to the previous two ones. All right. However, you want to construct a matrix U that contains 4 columns, right? U1, U2, and U4. Now you know that U3 orthogonal to the previous two, U4 is orthogonal to the previous two. These two guys are independent if you construct it from the null space of A transpose, right? Usually the first step is to get the, basis for null space of A transpose. So they are guaranteed to be independent. However, they are not necessarily mutually orthogonal. These two guys, if you just extract from any basis for null space of A transpose, these guys don't have to be orthogonal. That's why I can apply Gram-Schmidt procedure on these two guys on U. Let me just call it U3 and U4 tilde yet. Okay, these two guys I can apply Gram-Schmidt so that I get U3 and U4 that is now mutually orthogonal. Okay, and of course, as you know that uh, uh, after the Gram-Schmidt, this guy is also, because you do the Gram-Schmidt on U3 and U3 tilde and U4 tilde that are already orthogonal to U1 and U2. All right. The Gram-Schmidt is just another rearranging way of linear combinations. So after the Gram-Schmidt, the matrix U3 and U4 tilde is just linear combination of U3 tilde, U4 tilde. This is linear combination of U3 tilde, U4 tilde. Okay. So that's why it also guaranteed that after the Gram-Schmidt, this vector is still orthogonal to U1 and U2. But the main point of performing Gram-Schmidt is that to make U3 and U4 mutually orthogonal. So you can check from the value here. So once we have found 4 columns in U, we just stack them into columns in the matrix U, right? And this is so sorry, this is not supposed to be here. So this is not correct. Okay. The matrix sigma is supposed to be just this, right? So this is U, this is sigma 1, 0, and this is V transpose. Okay. And for the tall A, the thing that only matter to the calculation is the partition U1, sigma 1, and V transpose. Only U1 and sigma 1 are used. You can see that in this particular example, A has low rank. That's why you find that sigma 1, sigma 2, and sigma 3, you find one singular value that is 0. Okay. So this form can further reduce. Um, in those calculation of SVD, you see that when A is m by n, all right, A transpose A is going to have size of n by n. So the number of non-zero eigenvalue in A transpose A, it could be less than or equal to n. Okay, just in the previous example, right? In this one, so n is 3, right? The number of non-zero singular value is only 2, can be less than or equal to. So the reduced SVD form is to use only the portion of sigma 1 in the calculation. So for the tall case, as we said earlier, for the tall case, when you multiply these and these, we use only U1 and sigma 1. And for the fat case, you after you multiply this with this, you only use sigma 1 and V1 transpose. Okay. So okay, this is called the reduced form. Okay. So when you have I gave an example in the tall case. This is a matrix A, right? And this is U1, U2, this is sigma 1, 0, and V transpose. The reduced form of SVD is this, to use only U1 and sigma 1. U1, sigma 1, V transpose. However, however, it could be the chance that your R, the R is the number of non-zero singular value, okay? The number R could be less than n. When the number R could be less than n, it means that your sigma 1 can contain some 0 in the diagonals. It could be sigma 1, sigma R, and maybe, suppose that in this example, maybe you have another two zero singular value. In this case, you can further use partition your sigma 1 into the leading block that is non-zero in the diagonal, which means I illustrate with this picture here, okay? So this is in this example, this is my U1, this is my example in the tall case. This is sigma 1, this is 0. But my sigma 1 can contain 0 here, okay? So when I use the dark color, it means that it's non-zero. And the corresponding V can be V1, V1 transpose, and V2 transpose here. So after you perform a reduced form, you can further take the truncated form, which means I only use the portion of sigma 1 tilde, let's say the whole thing is sigma 1. I can further taken this part, multiply with this, and this is to get the truncated form. Okay. Maybe let's see this example again on the numerical example. Okay, so what I'm gonna do is I'm gonna generate a tall one, 5 by 3. Okay, but I'm gonna make the last column A is 5 by 3, so the rank of A is at most 3, but I'm just going to generate A such that in this example, my third column is the linear combination of the first two columns. So apparently my rank A must be 2. Okay, take the lecture, see the lecture again. The reduced one is going to be only taking the U1 partition, and U1 partition is going to be my A is m by n, right? My U1 partition is going to be m times the first n column, and this is going to be the remaining m minus n columns, right? So what in this example, what I'm going to do A, so I use the wrong variable. Okay, USV is the SVD of A, okay? So you can see that my sigma 1, which is 3 by 3, my U, my U1, my U1, U1 is m by n, okay? My U1 is going to be contain the first n columns. My sigma 1, okay, is going to be the first n by n upper block, right? So in this particular example, um, I'm going to take the reduced form. So I'm going to use only the first n column, which is 3. My A is 5 by 3, right? So I'm going to use the first 3 times the sigma, which is the upper block, 1, 2, 3. So I'm going to take the upper block and then times V transpose. And that give me the reduced form of the matrix A. All right. Now, let's talk about the truncate one. Okay, in this one, so the truncate one is to take the portion of U1, right? That's corresponding to the non-zero singular value. All right. So in this particular example, my U1 is the first 1, but because I know that the one that correspond to the non-zero singular value is going to be the first 2 columns. Let's see, USV. Okay, now I'm going to take the truncated form. So the one that is corresponding to do the lecture, all right? So now I'm gonna get only the first R columns. I'm gonna get and I'm gonna take in the R by R block, that is a subblock of n by n to this one, all right? And I'm gonna take, because I'm gonna take the first R rows in V transpose, which means this is gonna be the first R columns in V and then the transpose, right? This is the truncated one. So what I'm gonna do in the MATLAB would be, now I'm going to take the first R column, which is 1 to 2, right? And going to take the first R by R leading block, which is 1 over 2, 1 over 2. And then I'm going to get the first 1 to R column, which is 1 over 2, 1 to 2 columns, and then transpose. And this is going to be my uh, by truncated form of SVD. So now you can take a look that the results stay the same. Okay. Okay, so this is the SVD form, and we in the next video I'm gonna explain the SVD application in image compression and in principal component analysis.